Let me now go through an important remark. From the definition of an upper bound of a set, we see the following. A real number m is an upper bound of a set A if and only if, for all x in A, x is less than or equal to m. So what does it mean by a real number m prime is not an upper bound of a set A? We only need to take the negation of this statement. That means a real number m prime is not an upper bound of the set A if you can find some x in A such that x is strictly greater than m prime. Okay, so let me go through one example to emphasize this remark. Here, A is the open interval -1, 2. We can see that m equals 3 is an upper bound of this set because 3 is greater than or equal to every element of the set. However, m prime equals 1 is not an upper bound of this set. Why? Because we can find some element x in A such that x is strictly greater than m prime. For example, x equals 1.5. Then it is in A and it is strictly greater than m prime. Therefore, m prime is not an upper bound of the set A. How about m prime equals -2? Is it an upper bound of the set A? The answer is no, because again, you can find some x in A such that x is greater than -2. So again, I want to emphasize a very important fact that we are going to use later on. That is, a real number m prime is not an upper bound of a subset A of the real line if and only if you can find some x in A such that x is strictly greater than m prime. Let me now continue with a very important mathematical result that gives a characterization for the supremum of a set. Let A be a subset of the real line that is non-empty and bounded above. Then, as you know from the completeness section, the supremum of A exists as a real number. So, the real number alpha is the supremum of A if and only if the following conditions are satisfied. First of all, x is less than or equal to alpha for all x in A. That means alpha is an upper bound of A. And the second condition says that for any positive real number epsilon, there exists an element A in A such that alpha minus epsilon is strictly less than A. In this example, A is the interval -infinity to 2. As you know, alpha equals 2 is the supremum of the set A. Now, if you subtract a positive real number epsilon from alpha, then this proposition says that there should be some element A in A such that A is strictly greater than alpha minus epsilon. How can we prove this proposition? The proof is based on the remark that I stated earlier. So I'm going to recall it right now. A real number m prime is not an upper bound of A if and only if there exists some real number A in A such that A is strictly greater than m prime. So to prove this statement, first of all, we suppose that alpha is the supremum of A and then show that both A and B are satisfied. Suppose that again, alpha is the supremum of A. By the definition, we know that alpha has to be an upper bound of A. So x has to be less than or equal to alpha for all x in A. Therefore, the first property here is satisfied, obviously. But how come the second property here is also satisfied? Observe that alpha is the least upper bound of A. So anything that is less than alpha cannot be an upper bound of A. Now, alpha minus epsilon is strictly less than alpha. It is strictly less than alpha. Therefore, it cannot be an upper bound of A, again because alpha is the smallest or upper bound already. Okay. Now, because alpha minus epsilon is not an upper bound of A, by the remark stated here, there should be some element of A that is strictly greater than that number. So alpha minus epsilon here plays the role of M prime in this remark. So there should be some A in A such that A is strictly greater than alpha minus epsilon. The proof of the converse statement is also similar. You can look at the book, our textbook, for the detailed proof.